Footwork and balance, locomotion performance head-to-head. A humanoid robot can look impressive while walking in a clean, empty room. The real test begins when the robot must carry weight, climb stairs, recover from a push, cross uneven ground, and stop a slip before it becomes a fall. This article presents a fair benchmark for humanoid A and humanoid B. It covers walking, running, stairs, uneven terrain, energy use, push recovery, slip detection, balance control, and foot sensor accuracy. Important scope note: the prompt does not identify the two robots or provide raw trial data. Therefore, this article does not invent head-to-head results. It provides a complete test plan, the correct statistics, and a current comparison of real humanoid robots that could be used as humanoid A and humanoid B. The need for this kind of test is real. NIST is developing a new baseline benchmark for humanoid robots because the industry still lacks a common modern way to compare robots across mobility and physical tasks. Why locomotion needs a serious benchmark? Humanoid locomotion has several parts: speed, how fast can the robot move? Efficiency, how much energy does it use? Stability, can it stay upright when conditions change? Recovery, can it take a useful step after a push? Terrain skill, can it handle stairs, gaps, slopes, and uneven ground? Sensing, can it tell when its foot has touched, lifted, or slipped? Repeatability, can it do the same task again and again? A single successful video does not answer these questions. A robot may climb a staircase once, but fail on the 10th attempt. It may run quickly without a load, but slow down sharply while carrying a box. It may detect a slip only after the body has already begun to fall. Earlier research benchmarks show a better approach. The HRP2 humanoid study measured distance, success rate, time, energy, cost of transport, stairs, pushes, slopes, and uneven terrain. Define humanoid A and humanoid B. The two robots should be assigned test labels only after their exact versions are fixed. The test record should include. For the full table, please open this article on robotcomparisons.com. A factory robot and a research robot should not be compared without explaining the difference. For example, one robot may have a large industrial battery and heavy frame, while another may be a small, low-cost research platform. The main comparison should use the same absolute payload, such as the same 5 kg or 10 kg mass. A normalized payload expressed as a percentage of robot body mass. This prevents a large robot from appearing stronger, simply because it is much heavier. Identical load rules. The payload should have the same mass within a small laboratory tolerance. Use the same center of gravity as closely as possible. Be mounted in the same general body location. Be fixed so it cannot swing or shift. Stay below the safe limit of both robots. Be included in the total mass used for energy calculations. A rigid backpack or torso-mounted frame is usually better than a hand-carried box. A hand-carried box adds another variable: grip control. Test environment and safety. The test area should use an overhead safety tether, fall mats or a robot radon safety cage, a remote emergency stop, motion capture cameras, force plates or instrumented floor panels, a calibrated pusher, a friction measurement tool, battery and electrical power logging. The tether should stop a dangerous fall but should not hold the robot upright during normal movement. The test team should also record floor temperature, humidity, battery temperature, motor temperature, robot warm-up time, time between trials. These details matter because motor heating, battery voltage, and rubber sole temperature can change walking performance. Walking test. Flat ground walking. Use a straight, marked course of at least 10 meters. The robot should start from the same position each time and walk without human steering. Average speed, maximum stable speed, lateral drift, step length, step time, foot placement error, body sway, energy use, number of stops, number of failures, human interventions. The robot should be tested at several speeds. The highest speed should not be based on a single successful run. Definition of top speed. The benchmark should define top speed as the fastest measured speed at which the robot completes the full course in a preset number of successful trials without falling, stepping outside the lane, or receiving human help. For example, the test may require at least 8 successful runs out of 10. The rule must be chosen before testing. A robot that briefly reaches a high speed but cannot repeat it should not receive the same score as a robot that moves slightly slower but works reliably. Running test. Running should be separated from fast walking. For this benchmark, define running as movement that includes a true flight phase, meaning both feet briefly leave the ground. If the robot always keeps one foot on the ground, report the result as fast walking, not running. MARE, maximum sustainable running speed, acceleration time, stopping distance, step frequency, flight time, foot impact force, stability after stopping, energy use, failure rate. The robot should run over a short, straight course first. Turning and stopping should be tested separately because many robots can move quickly in a straight line but struggle when they must change direction. Sustainable speed. Fastest speed maintained over a longer distance without failure. The second number is more useful for warehouses, factories, and delivery work. Stair ascent and descent. Stairs are one of the best tests of foot placement and balance. They require the robot to handle vertical movement, changing support height, foot clearance, forward balance, backward balance, accurate contact sensing, higher motor loads. The primary test should use a fixed staircase with a known riser height, a known tread depth, at least 10 steps, no handrail, the same surface material for both robots. A second test may allow a handrail, but it must be reported separately. Measure ascent time, descent time, steps per second, vertical speed, foot placement error, toe strikes, heel strikes, double contacts, pauses, falls or emergency stops, energy per step, recovery after a missed or poor contact. Ascent and descent should never be combined into one score. A robot may climb well but descend slowly because descent requires better control of forward momentum. Earlier humanoid testing found that stair height changes the control problem. HRP2 used different strategies for 10-centimeter stairs, 15-centimeter stairs, and uneven paving stones. Uneven terrain traversal. Uneven terrain should be repeatable. A random pile of objects is difficult to compare because the two robots may receive different challenges. A good course can use modular blocks, uneven plates, small ramps, shallow gaps, randomized height changes, a repeatable gravel or rubber surface, a narrow beam section. The course should have several difficulty levels. For example, flat floor with small height changes, mixed height blocks, random foothold locations, low friction uneven ground, combined uneven ground and payload. Measure completion rate, average speed, maximum obstacle height, foot placement error, body pitch and roll, number of recovery steps, foot scuffing, slip distance, energy use, human interventions. Terrain should be reset between trials. If a block moves during one robot's run, its position must be restored before the other robot runs. NIST mobility research identifies slippage, uneven floors, heavy loads, vibrations, and force changes in position as important problems for mobile robots. Cost of transport. Speed alone is not enough. A robot that moves quickly but uses a great deal of energy may be expensive to operate. The standard cost of transport, or COT, is COT equals E divided by M times G times D, where E is energy used, M is total moving mass, G is gravity, D is distance traveled. For an electrical COT test, measure power at the battery or main DC power bus. E equals the integral of VT times IT. With respect to time, the measurement should include meters, computers, cameras, LiDAR, fans, pumps, batteries, and onboard electronics. Report both. Electrical COT, energy taken from the battery. Mechanical COT, positive mechanical work delivered by the joints. Electrical COT is more useful to a business owner because it reflects operating cost. Mechanical COT is useful for comparing the walking controller itself. For stairs, report energy per step, energy per vertical meter, total elevation gain, horizontal distance, ascent and descent separately. A robot can show a low COT on flat ground, but a very high COT on stairs. The benchmark must show both. Calibrated push recovery test. A human shove is not a good scientific test. Human pushes vary in force, direction, duration, and contact location. Use a motorized or pendulum-based pusher with a load cell. The pusher should measure the complete force curve. The key quantity is impulse. J equals the integral of f of t with respect to t. Report both. Peak force in newtons, total impulse in newton seconds. Impulse is important because a short, strong push and a longer, weaker push can have different effects, even when their peak force is similar. Push directions test. At least, forward, backward, left, right, forward right. Test the robot while standing, during normal walking, while carrying the standard load, on flat ground, on low friction ground. Recovery measurements. Define the following times. Push detection time, time from push onset to robot detection. First step time, time from push onset to the first recovery foot contact. Stable state time, time until the robot returns to a stable condition. Recovery step count, number of steps needed to stop the body motion. A successful recovery should require no fall, no tether support, no human intervention, completion of a 2-second stable period, no large uncontrolled foot slide. ZMP, capture point, and modern balance control. A robot's balance controller is often more important than its motor strength. ZMP control. The zero moment point, or ZMP, is a traditional balance idea. In simple terms, the robot tries to keep the combined ground reaction point inside the area supported by its feet. ZMP-based walking is useful for planned walking, slow and steady movement, predictable floors, stair patterns, footstep timing. The test should record measured ZMP or center of pressure, distance from the edge of the support area, ZMP tracking error, time spent outside the support area, changes during load carrying. ZMP and preview control methods remain important parts of humanoid walking research. Capture point control. The capture point estimates where the robot must place its next foot to stop its falling motion. A simple form is XCP equals XCOM plus VCOM divided by omega naught, where XCOM is the center of mass position, VCOM is center of mass speed. Omega O depends on gravity and center of mass height. A robot using capture point control should move its foot toward the predicted stopping location. The test can compare predicted capture point, actual recovery foot location, final stopping error, number of steps, recovery success. The capture point method was developed specifically to study humanoid push recovery and the question of when and where a robot should step. Learned and whole body control. Many newer robots use a mixture of model-based control, whole body optimization, model predictive control, reinforcement learning, imitation learning, and vision language action models. A benchmark should not assume that a robot uses ZMP or capture point merely because it walks well. Manufacturers should disclose the control structure, or the test should label it not publicly disclosed. For fair comparison, the report should state control update rate, sensor inputs, whether the controller uses a terrain map, whether the policy was trained on the test surface, whether the robot can slow down automatically, whether teleoperation is available as a fallback, whether the controller changes during a fall or slip. Slip detection on low-friction surfaces. Slip detection is a major test of real balance intelligence. The low-friction floor should be measured, not simply described as slippery. The test team should record the static and dynamic friction of the surface before each test session. A slip event should be confirmed using motion capture, force plates, foot-mounted markers, joint encoder data, and foot sensor data. A simple slip definition is tangential foot movement occurs while the foot is still carrying a meaningful vertical load. Slip test procedure. Start the robot at a known speed. Place one or both feet on the low-friction section. Use the same surface and friction level for both robots. Record the exact moment the foot begins to move. Record when the robot announces or reacts to the slip. Continue until the robot recovers or falls. Measure slip detection latency, slip distance before detection, false alarms, missed slips, recovery success, change in step length, change in body angle, time needed to return to normal walking. Low-friction walking is difficult because many walking controllers assume that the supporting foot does not move. Research on biped robots has shown that slip changes the robot's dynamics and can make ordinary balance controllers fail. Foot sensor fidelity. A foot sensor is not automatically accurate because it is present. Its readings must be compared with a trusted reference. Sensor types. For the full table, please open this article on robotcomparisons.com. Foot sensors should be calibrated at several points across the sole. The robot should be placed over a reference force plate so that the onboard sensor can be compared with laboratory ground truth. Measure. Vertical force error, horizontal force error, center of pressure error, contact onset delay, contact off delay, sensor noise, hysteresis, saturation, repeatability after repeated loading. Research on humanoid foot sensors shows that calibration is necessary for reliable center of pressure and ground reaction force measurements. Public product pages also show why careful testing is needed. Boston Dynamics lists tactile fingers and palm sensing for Atlas, but that does not prove the robot has a publicly documented force-sensing foot. Unitree lists dual joint encoders, a depth camera, and 3D LiDAR for G1, with optional tactile arrays for its hand, but does not publicly provide a full foot sensor accuracy report on the product page. Repeatability and statistical reporting. A strong test should use at least 15 valid trials per condition as a minimum, 20 trials per condition when practical, at least 3 separate test sessions, randomized robot order, randomized push direction and trial order, the same warm-up and battery state. A failed run must count as a failed run. It should not be removed simply because the robot did not finish. Required statistics. For the full table, please open this article on robotcomparisons.com. The final report should show both average performance and variation. A robot with a slightly slower average speed, but very small variation, may be more useful than a faster robot that often fails. Final results table. The completed study should use a table similar to this. For the full table, please open this article on robotcomparisons.com. Real humanoid robots that could fill the AB slots. Agility Robotics Digit is aimed at warehouses and industrial work. Agility describes it as a fully autonomous robot with commercial deployments, a 35-pound carrying capacity, and about 4 hours of battery life. The company also describes AI-powered learning, learning from demonstration methods, reinforcement learning, and a whole-body control foundation model for balance and movement. Agility has published demonstrations of Digit walking across challenging terrain, and has also shown running-related development. These are useful signs of capability, but they are not a replacement for a same-load, multi-trial benchmark with public averages and confidence intervals. Best fit, warehouse and factory evaluation. Boston Dynamics Atlas. The electric Atlas is positioned as an industrial humanoid rather than a consumer robot. Boston Dynamics lists a height of 9 meters, a mass of 90 kilograms, 56 degrees of freedom, 4 hours of battery life, 50 kilograms of instant weight capacity, and 30 kilograms of sustained weight capacity. It also lists tactile fingers and palm sensing and a 360-degree camera view. Atlas is being offered through a staged enterprise process. Boston Dynamics describes an initial customer pilot with Hyundai, select early adopters, autonomous navigation to a charging station, and automatic battery swapping. Best fit, high-end industrial automation, and enterprise pilot testing. Unitree G1 and G1 EDU. Unitree lists the G1 from $13,500 excluding tax and shipping. The standard G1 is listed at about 35 kilograms, with 23 degrees of freedom, about 2 hours of battery life, dual joint encoders, a depth camera, and 3D LiDAR. The EDU version offers more joints and optional computing hardware and hands. Unitree promotes imitation learning, reinforcement learning, force control hands, and its Unifal LEM robot model. The company also warns that some functions remain under development, and that individual users should understand the limitations of humanoid robots before buying. Best fit, research, education, and lower-cost physical AI development. Apptronik Apollo 2. Apptronik's Apollo 2 is aimed at industrial work. The company describes both bipedal and wheeled versions, swappable batteries, opportunity charging, and a goal of continuous operation. Apptronik also reports active Apollo 2 fleets at its robot park facility and at customer and partner sites, including Mercedes-Benz and GXO. The company is using teleoperation, simulation, and real-world data to train physical AI models in partnership with Google DeepMind. This makes Apollo a strong example of a robot where autonomy is being developed through a continuous data collection loop. Best fit, business owners evaluating industrial deployment and fleet learning. Figure 03. Figure's latest systems use Helix, a vision language action system that connects perception, movement, reasoning, touch, and proprioception. Figure reports that Helix 02 controls the entire body and has completed long-horizon tasks involving walking, manipulation, and balance without human intervention in demonstrations. Figure 03 arrived at BMW Group plant Spartanburg in June 2026, following an earlier Figure 02 deployment. Figure also reports commercial work with Catalyst Brands and Logistics. Best fit, AI-heavy industrial and logistics research. 1X Neo. 1X is focused on the home market. Neo Gamma uses reinforcement learning from human motion capture data for whole-body movement, with a reported 100 Hz control loop. The company describes internal home testing and an early access path for customers in 2026. Best fit, consumer and home robotics, although broad retail availability and independent performance data remain limited. What buyers should ask before choosing a robot? For consumers and researchers, ask for exact hardware and software version, real battery runtime under walking load, safe payload, not only peak payload, foot sensor type and calibration data, recovery performance after pushes, slip detection performance, whether the robot can be teleoperated, warranty and repair support, software development access, failure logs from real users. A low purchase price does not mean low total cost. A research robot may require additional safety equipment, programming time, replacement parts, and engineering support. For business owners, the most useful business measures are completed work per hour, human intervention minutes per hour, uptime, maintenance time, battery change time, safety incidents, energy cost per completed task, performance while carrying the real payload, floor and stair compatibility, recovery after contact with people or objects. A robot that wins a speed test but needs constant supervision may be less valuable than a slower robot that works all day with few interventions. Conclusion. A serious humanoid locomotion comparison must test more than a straight walk. The winning robot should combine high repeatable speed, low energy use, reliable stair ascent and descent, strong uneven terrain performance, fast push recovery, early slip detection, accurate foot sensing, few human interventions, stable performance across many trials. At present, the humanoid market contains very different products. Digit, Atlas, Apollo 2, and Figure 03 are moving toward enterprise deployments. Unitree G1 is more accessible to researchers and advanced users. 1X Neo is aimed at early home access. Their public demonstrations show rapid progress, but they do not yet provide a complete, independent, same load, same floor, multi-trial comparison. That is why the benchmark matters. The future leader will not be the robot with the most impressive video. It will be the robot that can repeat difficult physical work safely, efficiently, and predictably. All links to sources are available in the text version of this article. You can find the full article at robotcomparisons.com/blog. Thanks for listening. Thanks for listening to Robot Comparisons. If you found this episode valuable, make sure to subscribe so you never miss a new deep dive. For the full written breakdown, detailed spec sheets, and side-by-side comparisons, head over to robotcomparisons.com. That's ROBOTCOMPARISONS.com. New research drops multiple times a week.